Alright, so we're going to look at a second differential equation type problem involving a velocity dependent force. In this case we have a vehicle that's driving along, we'll say it's a car, it's driving along at some velocity v. When they let off of the gas and they begin to slow down, and let's say they experience a force that is proportional to v squared, and so they're going to be slowed by some backward force b v squared. So if this is normal force, right, the weight, and so I have this backward force bv squared. And so again, like before, we want to find an equation for the acceleration, or for the velocity. And so in this case we wouldn't find terminal velocity because it's got this max speed and it's slowing to a stop, right? In this case the car is going to come to a stop, and so we have a max velocity, we'll call it v naught. And so we want to solve this problem. This one our answer is going to be a little bit messy, but we don't have to use natural logs in this case. So in this one we're going to do a net force equation, ma equal to bv squared. We're going to negative bv squared, sorry. So we're going to start with just writing a differential equation here. So we're going to replace a with m, so dv dt equal to negative bv squared. We'll divide the m over, and we get that dv dt is equal to negative bv squared over m. Okay, so we've done the first part. We wrote that differential equation. Part 2 is going to be the separation of variables. And so part 1, part 2, we're going to multiply the dt over there and divide the v squared over. This one's a little easier because we can just divide that v squared over. So that we get dv over v equal to negative, sorry, this is v squared, b over m dt. Okay, and so now we have separated the variables. The next step, step 3, is to integrate. We're going to bring it over here. So we're going to integrate dv over v squared, and we're going to go from v naught to v, and we're going to integrate the negative b over m dt, and we're going to go from 0 to t. Okay, and so this one we just end up with negative b over m times t. We're good there. In this case, the integral of 1 over v squared is going to be negative 1 over v, and we're going to evaluate this from v naught to v. And so we evaluate this from negative 1 over v minus negative 1 over v naught. This will become a plus right here, equal to negative b over m times t. So we'll subtract this over to the other side, and we get negative 1 over v equal to negative b over m t minus 1 over v naught. Okay, and so because they all have a negative sign, we'll just multiply the whole thing by negative 1, make that a little easier. 1 over v equal to b over m t plus 1 over v naught. So the next step here to get v on the top is we take the reciprocal of both sides. We get v equals 1 over, so 1 over b over m t plus 1 over v naught. So v is equal to all of this. And so the way to think about it is if we plug in a really small number for t, so we plug in 0, we get 1 over 0 plus 1 over v naught, and all that just simplifies to v naught. So when t is 0, we end up with v naught. If t is really big, like 100, it becomes 1 over 100 plus v naught, and so this is going to end up being something really small because we have a really big number in the denominator here. Okay, and so as t grows, our velocity gets smaller, which makes sense because this car is slowing down. Okay, we can graph this, and so we have a velocity time graph. We start from our velocity v naught, and then we're going to approach 0. Okay, You can do it. I'm not very good at approaching 0 for some reason. I don't know. Okay, and so next step, just like before, is we're going to now take the derivative to get our velocity. So we have v is equal to 1 over b over mt plus 1 over v naught. And so we want to take the derivative with respect to t. So dv dt is our acceleration. And so to do this, we're going to take the chain rule, or use the chain rule. So we'll take the derivative of this inner part. We get b over m as the derivative of this lower part here. Then we take the derivative of the whole thing. So let's see, b over mt plus 1 over v naught to the power of 0, or to the power of -1. We multiply the negative in front, and then that becomes a -2. And so then it's 1 over b over mt plus 1 over v naught, and this whole thing is squared. Okay, and that's our equation for acceleration. Okay, it's a little bit uglier, but that is our acceleration. Okay, and so if we're going to graph this, we do need to know what our starting value for acceleration is. But just like the previous one, our acceleration is also going to approach 0 because this object is slowing down. Okay, and so if we're going to plot acceleration over time, we would say, okay, let's plug in a 0 there. So 1 over 0 plus 1 over v naught, and this is all squared, times negative b over m. And this is basically going to become negative b over m times v squared. And so our starting value, negative b over m v squared, it's going to approach 0 as well. Okay, so that could be a graph of our acceleration. And then if we want to graph our position, well, we're going to start out with a positive velocity. So we have a positive slope, and then it's going to eventually approach a velocity of 0, so it's going to come to a stop. Okay, and so this is our second equation or question that we did involving differential equations. So first step again was to write our differential equation. The second step was to do the separation of the variables, and the third step was to solve it. And then we did these different graphs that we looked at, and we're not going to mess with this one right now, but hopefully you kind of get the idea. Okay, so let me know if you have any questions.